All right, hello and welcome back. So this is another ALEKS topic that's called Understanding Consequences of Important Physical Properties. And this was a requested video, so thank you very much for the request. If there are other ALEKS topics that you would like me to make videos for and you can't find them on my channel, definitely let me know. You can comment below and I'll try to get them made as quickly as I can. No guarantees that I'll be that day, but I'll again try to get them done as quickly as I can. So this topic I think is a good topic because it relates our physical properties to one another, but also to intermolecular forces, the idea of intermolecular forces. There are some confusing aspects to this topic, so I'm going to go through a variety of different examples. I'll do 3 different examples, the last one being sort of the most confusing one, where it seems a little bit, it could be interpreted as contradictory, but I think we'll figure it out. So let's go ahead and get started. The first thing that I would do when I first start doing these problems is I would read the first sentence and try to draw a conclusion about the relative intermolecular forces at play. So it says liquid X is known to have a lower surface tension and lower viscosity than liquid Y. So both of those suggest that liquid Y is more stuck together. And I know this is sort of a crude way together. It's a crude way to think about these different liquids, but I think that it gets to the point, right? And it gives us a really good sort of idea of what we mean when we say it's got higher intermolecular forces. So if we want to be a little bit more sciencey, we could write higher intermolecular forces. But more stuck together means that, if my hands are the different molecules of Y, they're going to be more stuck together. To pull them apart, it's going to take more energy than the molecules of X. So I think it's a good way for us to visually or just think about what's going on. All right, so let's go ahead and talk about what's going on over here. It says wax-coated particles are carefully put on the surface of liquid X or liquid Y. So if we draw sort of, again, a crude little diagram, this is liquid X. This is liquid Y, and then I'm going to put this sort of like bead or little ball of wax on the surface, and then I'm going to see how big I can make that bead until it falls down, or I can make that little piece of wax until it falls down to the bottom. So this is going to be a measure of surface tension. The higher the surface tension, the sort of more force you're going to have to push down to break that surface. So since Y is more stuck together, higher intermolecular forces, it's got a higher surface tension than liquid X. The mass of that particle is going to be bigger for liquid Y before it falls down to the bottom than liquid X. Liquid X is going to have a lower surface tension, so it can sort of push out of the way those particles a little bit easier, and therefore the mass of X will be less than the mass of Y. Identical wire loops are dipped into liquid X and liquid Y, so film forms. So I think this one again is related to the surface tension. It's going to be saying we've got sort of a bubble, and then we're gonna spread it out. We're gonna pull on that, and again that's going to be related to surface tension. To pull on that, on all those molecules forming that bubble. I'm imagining a bubble, just like a bubble wand in between my hands, and if I pull on that, that means I'm pulling all those molecules apart from one another. And to pull those molecules apart from one another, if they're more stuck together, it's going to take more energy to do that. If they're less stuck together, it's going to take less energy to do that. So f of X will be less than f of Y because X is less stuck together, has a lower surface tension than those Y molecules. All right, so let's go ahead and move on to the next one. Like I said, we're going to do 3 of these to go through a variety of different examples. Again, in this one, liquid X is known to have a lower surface tension, lower viscosity. So in general, we could say Y is more stuck together again, same thing with the intermolecular forces. It's going to have stronger intermolecular forces, higher intermolecular forces. Liquid X and liquid Y are each pumped through tubes. So my little crude diagram for this, I'm going to have a liquid in the tube, and I'm going to push it out until it comes out the other side. So if Y is more stuck together, it makes sense that it's going to take more force to push that through. Therefore, the Px will be less than Py. The force, that's the pressure that you're going to need to push through that liquid, is going to be less for Px than Py as I push that liquid through. This next one, this is actually talking about the density. So it says we got 50 milliliters of X, 50 milliliters of Y. We're going to mix them together, see what happens. And these outcomes, these are really based off of density. X will form a layer on Y, Y will form a layer on X. That's related to the density. This one is related to the sort of type of intermolecular forces that we'd find. Are these polar molecules or non-polar molecules? We don't have that information, right? We don't actually know what the densities of these are, and the intermolecular forces are not going to be related to the density at all. So it's impossible to predict this one. We're not going to be able to tell, based on the information that's given, what the relative densities are going to be, or if they're going to have similar intermolecular forces in terms of is one nonpolar or is one polar, right? There could be differences, so we don't know that one. Okay, the last one, and this is the one that could be a little bit confusing because it seems like the information that's given is contradictory. Sort of in our crude way that we're thinking about this, where I say liquid A is known to have a higher surface tension and higher vapor pressure, you might say, well, higher surface tension means that it's more stuck together, but higher vapor pressure would actually mean that it's less stuck together. With our sort of fundamental knowledge about vapor pressure, the less stuck together it's going to be, the higher the vapor pressure is going to be. So vapor pressure will be a measure. If I had 2 watch glasses, here's A and here's B. Liquid A is known to have a higher vapor pressure. So a higher vapor pressure means that more of it is going to be evaporating than for liquid B. So this is just to indicate how much of liquid A is evaporating. So let's say I've got my little layer of A, my little layer of B. More of A is going to be evaporating. It's got a higher vapor pressure than liquid B. So that's what vapor pressure is. Now, I actually did some reading on this, and I guess vapor pressure and surface tension are not going to be directly related. So you could have a higher vapor pressure and a higher surface tension, as it turns out. So we're really going to, this is a trickier version. We're going to have to sort of relate these experiments and which of these properties we're really talking about to understand, what's going on. So the first one, it says we're going to put liquid A and liquid B into a sealed flask. We're going to lower the pressure and then see which one is going to boil first. Well, boiling is when the vapor pressure is equal to the atmospheric pressure, and we know that liquid A has a higher vapor pressure, so it's going to boil more quickly, right? If it already has a higher vapor pressure, we're going to get to that boiling point more quickly. So eventually both liquids boil, A first and then B, and again, that's based off of this higher vapor pressure. The last one here, 2 10-liter glass flasks are evacuated and sealed. 40 milliliters are put into each of the different flasks. And then after 30 minutes, the pressures are measured. So again, the higher vapor pressure is going to lead to a higher partial pressure, all other things being equal. PA will be greater than PB because that vapor pressure is higher. So both of these questions really were using this higher vapor pressure aspect of this question. So if you get one that's like this and these properties seem contradictory, check with the experiments to make sure, to figure out which property they're sort of related to. These were both related to the higher vapor pressure, so I was able to answer the questions just based off of that. And I didn't have to worry about the higher surface tension, but yeah, hopefully that's helpful. And let me know if you got any other topics that you'd like me to make videos for. Cheers.